On October 16, 2025, a jaw-dropping image of 3I Atlas hit the scientific community like a thunderclap, deepening a mystery that already had astronomers scratching their heads. In this snapshot, 3I Atlas unleashes a 6,000-kilometer plume, aimed straight at the sun, completely backward from what nature should allow. This isn't just weird. It's the kind of unnatural that screams something built, not born. So what is this thing? Is it really a comet? Tonight, we're peeling back the layers of evidence one by one. And by the time we're done, what we uncover won't just rewrite comet physics, it'll drop a revelation that no one saw coming. If these mysteries pull at you the way they pull at me, don't just sit back, get in the game. Hit that like button, subscribe, and you'll catch every twist as this story unfolds live. Drop a comment telling me where you're watching from, what time it is there, and whether you think we're getting the full truth or just the version they want us to swallow. And if you want to blow this thing wide open, share it on X, Facebook, Reddit, or even in your group chats. This channel exists because of you, and your support fuels our hunt for the mysteries no one else dares to touch. Part 1. The image. That shouldn't exist. October 16th, 2025, a date that'll go down in astronomy history. The astronomical world got rocked by something that should have been impossible. An image dropped in the astronomer's telegram, processed from data collected August 2nd and 3rd by the Tidy Demeter's twin telescope in the Canary Islands. What it showed was so fundamentally wrong, so physics-stiffingly backward, that astronomers worldwide froze mid-task and stared. Picture this. At the center, a black circular mask blocks out the blinding glare of the object itself. Round it, a bright halo spreads the dusty coma you'd expect from any self-respecting comet. But then, extending from that cloud of gas and dust, there's something else. A narrow jet, faint but unmistakable, stretching about 6,000 kilometers in projection. And here's where physics throws its hands up. Okay, this jet points dead center at the sun. You might think big deal comets have jets all the time. They're spectacular, dramatic sprays of material as frozen volatiles vaporize under solar heat. But here's the kicker. Every undergrad astronomy student learns in their first planetary science class, comet jets always, and I mean always, point away from the sun. That's not a preference. It's a law. Radiation pressure and solar wind push outward. The physics is as simple as water flowing downhill, except here, the water's climbing uphill. 3 Atlas, this interstellar visitor that's had observers hooked for months, breaks that basic rule. Imagine watching a fountain, where the water arcs backward into the nozzle, or smoke from a fire drifting down into the flames. That's how wrong this is. The anti-solar direction, where jets and tails should thrive, sits empty or dim. Meanwhile, this sunward plume extends like an accusing finger at our star. Scientists live by models, frameworks that explain what we see, predict what's next, and sometimes crumble when nature throws a curveball. This image doesn't just challenge the comet model, it shatters it. If this feature is real, if it's not some elaborate image processing trick or observational artifact, then we need to tear up the textbook on how these ancient travelers behave. The implications ripple outward like cracks in ice. Are we looking at a whole new class of object? Is there some exotic physical process at play we've never seen in our solar system's comets? Or could this be evidence of something even stranger, something that makes comet feel like the wrong word entirely? These questions don't have easy answers, and that's what makes this moment so electrifying. Before we dive deeper, let's acknowledge the elephant in the room. Astronomical images, especially those teased from faint signals with fancy processing, can lie. They can show ghosts, artifacts, patterns that exist only in math, not in reality. Laplace filtering, the technique used here to enhance faint structures, powerful but not foolproof. It can amplify noise, create false features from background stars trailing across long exposures. Every astronomer worth their salt knows this, and the first response to any shocking image is healthy skepticism. So we're not buying this blindly. We're demanding confirmation, multiple independent observations. Different instruments and techniques, all pointing to the same conclusion. But I'll tell you this, confirmation exists. It's been building for weeks. Earlier observations hinted at plumes at odd angles, position angles around 280 that didn't match expectations. The Hubble Space Telescope caught glimpses of asymmetric features. Ground-based telescopes in multiple countries saw similar hints. This isn't one telescope having a bad day, it's multiple eyes on the sky, different technologies, all seeing something similar. The community hasn't reached absolute certainty. Science rarely offers that luxury. But the consensus is shifting from probably an artifact to likely genuine to we need to explain this thing. When astronomers start publishing papers, treating the sunward jet as real and demanding explanations, you know we've crossed a threshold. We've moved from skepticism to acceptance, from dismissal to fascination. What comes next will decide whether this object rewrites our understanding of small bodies in space or opens doors we didn't even know existed. The clock's ticking. Within days, 2 spacecraft will sweep through nearby space, their instruments, potentially capturing data that could confirm or demolish our interpretations. But before that moment, we need to grasp how deep this rabbit hole goes, because the sunward jet, that's just the beginning. The chemistry pouring out of this thing tells a story that makes the jet look almost mundane by comparison. Before we let ourselves believe in the impossible, we've got to rule out every boring explanation. That's the scientific method's greatest gift and its most frustrating demand. When you see something extraordinary, your first job isn't to celebrate, it's to doubt. So let's doubt intelligently. Image processing in astronomy is part art, part science, part forensic investigation. You're taking photons that journeyed across interstellar space, hit a detector, became electronic signals, and now you're mathematically manipulating those signals to reveal structures too faint for the naked eye. Every step opens the door for error. Background noise can masquerade as real features. Cosmic rays striking your detector leave bright streaks that look like jets. Stars trailing across long exposures create lines that might, by pure chance, align with interesting directions. Deconvolution algorithms, which try to sharpen blurry images, can ring artifacts in ways that generate false structures. The teams analyzing 3i Atlas know all this. They've been doing this for decades. They didn't just run the image through a filter and call it a day. They checked for background star contamination. They examined multiple observation epochs, To see if the feature persisted or changed in ways consistent with a real physical plume versus a processing ghost, they compared results from different telescopes with different optics, detectors, and atmospheric conditions. They looked at the raw data before any processing, searching for the faint signal that would confirm something real existed before enhancement algorithms touched it. What emerged from this gauntlet of skepticism was increasingly hard to dismiss. Earlier observations in late July and early August had already hinted at peculiar plumes at position angles that shouldn't make sense for normal cometary activity. Position angle, for those unfamiliar, is how we measure direction on the sky's 0 points north, 90 east, and so on. The anti-solar direction, where comet tails traditionally point, sits at a predictable angle based on the comet's orbit and the sun's location. For 3I Atlas, during those observations, that anti-solar direction was nowhere near where this jet appeared. Multiple research groups started cross-checking their data. The Hubble Space Telescope, with its exquisite resolution above Earth's turbulent atmosphere, captured images showing asymmetric coma structure. Ground-based observatories in Spain, Chile, and Hawaii independently noted unusual features. None of this happened in a vacuum. Astronomers talk, share data, compare notes. When multiple independent teams start seeing similar oddities, the artifact explanation gets stretched thin. Think of it like witnesses to a bizarre event. If one person tells you they saw something strange, you're right to be skeptical. If 10 people scattered across a city all described the same strange thing from different angles, using different cameras at slightly different times, but with consistent details, now you're obligated to take it seriously. That's where we are with the sunward jet. Too many eyes, too many instruments, too much consistency. The technical details matter because they separate wild speculation from grounded observation. When scientists use Laplace filtering, they're essentially looking for edges and brightness discontinuities. It's like cranking up the contrast on an image to make faint details pop. But that technique is well understood. We know its artifacts. We know how to distinguish real features from filter-induced ghosts. The sunward jet shows characteristics consistent with a real three-dimensional structure extending from the nucleus, not a flat processing artifact. Some researchers went further, analyzing the spectral signature of material in different parts of the coma. If the jet is real, its spectrum should show the same molecular emissions as the rest of the coma, just in different ratios, depending on what's being preferentially ejected. And sure enough, spectroscopic data supported the presence of material in that sunward direction, not just empty sky with noise. You can't fake molecular emission lines easily. Either the molecules are there fluorescing in sunlight, or they're not. So where does this leave us? The scientific community has moved from initial disbelief to cautious acceptance. Papers are being written that assume the sunward jet is real and focus on explaining it rather than explaining it away. That's a significant shift. It means we've crossed the threshold from "is it real?" to "okay, it's probably real, so what does it mean?" And that second question is far more interesting and far more unsettling. Because if the jet is real, if material is truly streaming toward the sun in defiance of everything we thought we knew about cometary physics, then we need to ask what's coming out of it. We need to look at the chemistry, the composition, the fingerprints of whatever substance is creating this backward fountain. And when we turn our spectrometers toward 3I Atlas and analyze the light it emits, we find something almost as strange as the jet itself. We find nickel where there should be iron, carbon dioxide where there should be water, and ratios that make no sense for a normal comet. The jet might be the most visually striking anomaly, but the chemistry, that's where things get truly weird. If the jet is real land, we're growing more confident by the day, then the next question becomes unavoidable. What exactly is streaming out of this thing? When we study comets, we're essentially doing cosmic forensic chemistry from a distance. Light from the sun strikes some molecules in the coma, exciting them to higher energy states. As they relax back down, they emit photons at very specific wavelengths. Each molecule has its own unique fingerprint, a spectrum as distinctive as a barcode. By spreading that light into its component colors and measuring the intensity at different wavelengths, we can identify what chemicals are present and in what relative amounts. Astronomers pointed some of humanity's most powerful spectrographs at 3I Atlas, the Very Large Telescope in Chile, equipped with a UV spectrograph, captured high-resolution spectra across multiple epochs as the comet approached the sun. What those spectra revealed was, to put it mildly, jaw-dropping. Strong emission from neutral nickel atoms dominated certain parts of the spectrum. This wasn't a subtle hint or a marginal detection. This was a clear, unambiguous signal shouting, "Nickel is here." Now, finding metals in comets isn't inherently shocking. Comets contain dust grains, and those grains include refractory elements, things like iron, magnesium, sodium, nickel, and calcium. When dust sublimates, or when solar radiation gets intense enough, these metals can appear in the gas phase and emit their characteristic spectral lines. What's shocking about 3I Atlas is the ratio. Specifically, the nickel-to-iron ratio makes no sense. In normal solar system comets, when you detect nickel, you also detect iron, and you detect it in ratios that roughly reflect cosmic abundances. Iron is more common than nickel in the universe. It's more common in meteorites. It's more common in practically every astronomical context we've ever studied. You expect to see more iron than nickel, not the other way around. But in 3I Atlas, observers found epochs where nickel emission was strong and iron emission was nearly absent. Not just a little weaker absent, gone, missing in action. The technical term scientists use is extreme abundance ratio. That's academic speak, for this is really, really weird. Some observations showed nickel-to-iron ratios orders of magnitude higher than anything seen in other comets. It's as if someone took a normal comet, carefully filtered out most of the iron and left the nickel behind. Nature doesn't usually operate with that kind of selectivity. But wait, the chemistry gets stranger. The James Webb Space Telescope, that marvel of infrared astronomy, revolutionizing our view of the interstellar, its instruments toward 3I Atlas JWST, specializes in infrared wavelengths, perfect for detecting molecules like water, carbon monoxide, and carbon dioxide. What it found was a coma dominated not by water, as you'd expect from a typical comet, but by carbon dioxide. The carbon dioxide to water mixing ratio came in at roughly 8:1. Let me say that again. 8 times more carbon dioxide than water. For context, most solar system comets are essentially dirty snowballs with water, ice as the dominant volatile. Sure, they contain carbon monoxide, carbon dioxide, methane, ammonia, and other frozen gases, but water usually wins by a comfortable margin. It's the substance that sublimates most readily at the distances where comets typically become active. Comets with high carbon dioxide ratios exist, but they're rare. And even among those unusual cases, 8:1 stands out as extreme. What could cause such odd chemistry? Scientists immediately began proposing natural mechanisms. One intriguing possibility involves metal carbonyl compounds. These are molecules where metal atoms bond with carbon monoxide groups. Nickel tetracarbonyl with the formula Ni carbon monoxide 4 is a real chemical that forms under certain conditions. Iron pentacarbonyl Phi carbon pentocarbon 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 is its iron analog. Both are volatile, meaning they can sublimate at relatively low temperatures compared to pure metals. If 3I Atlas somehow contained these compounds, their breakdown could release nickel and iron atoms along with carbon monoxide. The problem is that forming these compounds requires specific conditions, and maintaining them over the billions of years this object has spent in interstellar space. Metal carbonyls aren't particularly stable. They decompose when exposed to ultraviolet radiation, which is abundant in space. They require cold, reducing environments to form in the first place. Could 3I Atlas have formed in some exotic, stellar environment where these compounds were common? Perhaps around a carbon-rich star or in a molecular cloud with unusual chemistry. It's possible, but it's speculative. And that still doesn't fully explain the nickel-to-iron ratio. Even if metal carbonyls are involved, why would nickel carbonyls sublimate preferentially over iron carbonyls? The sublimation temperatures are different, but not dramatically. So you'd need a very specific thermal environment in the nucleus to drive nickel out while keeping iron locked away. And then, as the comet gets closer to the sun and temperatures rise, iron should start appearing, which it does, according to some observations. Researchers noted that iron emission became detectable only when 3I Atlas crossed inside about 2.64 astronomical units from the sun. That's consistent with a temperature-dependent release mechanism, but it requires a very specific layering or composition gradient in the nucleus. Some resetters, probably over late-night coffee in observatory break rooms, began whispering more exotic possibilities. What if some part of this object isn't natural? What if we're looking at materials that were processed or engineered? Nickel alloys are ubiquitous in human technology. Stainless steel, superalloys, 4 turbines, corrosion-resistant coatings all use nickel. Nickel cyanide chemistry is used in If you wanted to build a spacecraft or probe designed to survive interstellar travel, you might use nickel-rich alloys for their strength and resistance to corrosion. This is where we have to be very, very careful. The leap from unusual chemistry to alien artifact is enormous and requires extraordinary evidence. We have unusual chemistry. We do not have extraordinary evidence. But the question lingers uncomfortable and tantalizing in the back of every presentation and paper. If this chemistry is natural, it's teaching us that our models of comet formation are incomplete. If it's not natural, well, then we're having a very different conversation. The composition anomalies don't exist in isolation. They're part of a larger pattern, a web of strangeness that includes the sunward jet, unusual activity patterns, and other oddities we're only beginning to catalogue. When you start stacking anomalies, when you accumulate enough things that don't quite fit, you reach a tipping point where dismissing each one individually becomes harder than confronting them as a collective puzzle. And speaking of patterns, there's one more aspect of 3I Atlas's behavior that defies easy explanation. This object doesn't just emit gas randomly, it pulses. The object doesn't just spit gas into space in the gradual, continuous way we expect from sublimating ice. It does so like clockwork. Observers monitoring 3I Atlas detected periodicities in its brightness and outgassing activity rhythmic. Variations that repeat roughly every 4 hours. Some data hints at a 2-hour period as well, possibly harmonically related. Picture a heartbeat, a regular pulse that speaks of some underlying mechanism driving activity on and off with mechanical precision. In nature, regular periodicities usually arise from rotation. The most straightforward explanation for a comet showing a 4-hour activity cycle is that its nucleus spins with a 4-hour rotation period, and active regions on its surface come in and out of sunlight as it turns. This isn't unprecedented. Many comet nuclei are elongated, irregular, chunks of ice and rock that tumble through space. If jets are concentrated in certain areas, perhaps where volatile-rich deposits are exposed, or where the surface structure funnels gas, preferentially then as the nucleus rotates, those jets turn on and off relative to our line of sight or relative to solar illumination. This is a perfectly reasonable, perfectly natural explanation. Comets with periodic outbursts are known. The rotation explanation makes sense, and if that's all that's happening here, then the 4-hour pulse is interesting, but not paradigm shift. It tells us something about the shape and activity distribution of the nucleus, adds to our understanding of this particular object, but doesn't challenge fundamental physics. But let's dig a little deeper into what that explanation requires. For rotation to produce a clean, regular 4-hour signal in brightness and gas production, you need a very consistent active region or a very specific geometry. Small irregularities in the nucleus shape, uneven heating, changes in the subsurface ice distribution as volatiles deplete. All of these should introduce noise and variation. Yet, the observations suggest a remarkably stable periodicity. That's not impossible, but it's noteworthy. It suggests either that the nucleus is surprisingly homogeneous in its activity pattern, or that whatever's driving the outburst is self-regulating in some way. Another natural possibility involves a binary nucleus, 2 chunks of ice, orbiting each other. If the orbital period is 4 hours, tidal forces and mutual heating could drive periodic variations in activity. Binary comets and asteroids exist. We've observed them. The physics is well understood. If 3I Atlas is a contact binary or a separated binary, that could explain the periodicity without invoking anything exotic. But again, you'd need a fairly specific configuration, and we don't have direct imaging of the nucleus to confirm or rule this out. The object is too far away and too faint for even our best telescopes to resolve its nucleus directly. There's also the question of observational bias. Periodicities can be artifacts of how we sample data. If telescopes observe at regular intervals due to scheduling constraints or Earth's rotation, they might impose a false periodicity on noisy data. Astronomers know this and try to correct for it using statistical techniques. But it's always a concern. Could the 4-hour period be real in the data but not real in the comet? Possibly. The fact that multiple independent observing campaigns seem to see consistent timing argues against pure artifact, but we should remain cautious. Now, let's entertain the speculative sides, the interpretations that push beyond standard comet physics. If the 4-hour pulse is real and not simply explained by rotation or binarity, what else could cause it? Could there be some internal mechanism, some reservoir of volatiles being periodically released through a controlled vent in a natural comet? Internal pressure builds as ice sublimates below the surface, and eventually it breaches through weak points, creating outbursts. But those outbursts are usually chaotic, irregular, driven by fractures and collapses that don't follow neat schedules. A regular, sustained 4-hour cycle suggests either an extraordinary coincidence of natural factors or something more organized. Imagine if the nucleus had internal Strode chambers, or pockets, where gas accumulates and then releases when pressure reaches a threshold. If those chambers were similar in size and the sublimation rate was steady, you might get periodic releases. It's like a geyser, where groundwater heating follows a predictable cycle based on reservoir size and heat input. But comets aren't geysers. They don't have stable underground cavities and regulated heat sources. They're rubble piles of ice and rock, porous and crumbly, not plumbed systems with valves and chambers. And here's where we veer into speculative territory. The object has some engineered component. If part of the structure includes materials or design elements meant to regulate gas release, you could imagine a periodic cycle driven by intentional mechanisms. Vents that open and close, reservoirs that fill and empty, systems designed to maintain pressure or ration volatiles for long-duration travel. This sounds like science fiction because it is science fiction, at least until we have evidence to support it. But the 4-hour pulse, combined with the sunward jet and the nickel-dominated chemistry, stacks another anomaly onto the pile. There's one more angle to consider. If metal carbonyl compounds are involved in the outgassing, and if their formation or breakdown follows a cyclic chemical process that could introduce periodicity, imagine a feedback loop where heating drives sublimation. Sublimation cools the surface. Cooling allows carbonyls to recondense, and the cycle repeats. It's thermodynamically plausible if you have the right conditions, but again, this requires very specific chemistry and very stable conditions across the nucleus. It's not the first explanation you'd reach for, but it's not impossible. The 4-hour pulse matters because it's another data point that doesn't comfortably fit standard models. Taken alone, it's intriguing but explainable. Taken with everything else, it amplifies the sense that 3i Atlas is playing by different rules, and we're about to find out whether those rules apply only to this object or hint at a broader category of interstellar visitors. We've barely begun to understand. Because here's the urgent reality: we're not going to study this object leisurely over decades. We have one chance, one narrow window to get close-up data from spacecraft that happen to be in the right place at the right time. That window is opening right now, and within days, instruments aboard 2 missions will sweep through nearby space with their sensors pointed at this enigma. What they find or fail to find will shape our interpretation for years to come. This may be our only chance to see it up close. In the vast emptiness of space, encounters between human-made spacecraft and celestial objects are rare, precious opportunities, orchestrated by decades of planning or seized by fortunate timing. 3I Atlas arrived in our solar system unannounced, following an orbit we didn't predict, visible only after it rounded the sun and began its outbound journey. We can't send a mission to rendezvous with it. There's no time to design, build, and launch a probe that could catch up to an object already accelerating back toward interstellar space. But through a stroke of cosmic luck, 2 spacecraft launched for entirely different missions will pass within detectable range during the critical period when the comet is still observable. The European Space Agency's Hera mission design to study the aftermath of NASA's DART impact on the asteroid Dimorphos has a flyby window between October 25th and November 1st, 2025. During this period, Hera will pass within roughly 8 million kilometers of 3I Atlas. That's not close by spacecraft standards. Not a true flyby in the sense of skimming past at close range. But it's close enough for certain instruments to gather valuable data. Hera carries cameras, spectrometers, and particle detectors designed to study asteroid surfaces and dust environments. Those same instruments can be retargeted, at least partially, to observe the comet's coma and tail structure. NASA's Europa Clipper, en route to Jupiter's ice-covered moon, has a similar opportunity between October 30th and November 6th. Again, we're talking millions of kilometers, not hundreds or thousands. Europa Clipper won't resolve the nucleus. It won't take close-up images showing surface details, but its spectrometers can analyze the light passing through the coma. Its plasma instruments can detect charged particles stripped from the comet by the solar wind. Its magnetometers might pick up signatures of magnetic draping where the interplanetary magnetic field bends around the comet's ionized gas cloud. What makes these flybys particularly valuable is the diversity of measurements they can provide. Optical imaging from Earth captures the large-scale structure the jets and coma but can't easily distinguish between different chemical species or measure the physical properties of dust grains. Spectroscopy from ground-based telescopes gives US composition, but with limitations imposed by Earth's atmosphere and the comet's brightness. Spacecraft instruments, even at significant distances, can access wavelengths blocked by our atmosphere, measure particles directly, and observe without the blurring and scattering that plague ground-based observations. If either Hera or Europa Clipper detects strong nickel emission, that would independently confirm the spectroscopic oddities seen from Earth. If they map the comet's structure and find asymmetries consistent with the sunward jet, that strengthens the case for a real physical feature rather than a processing artifact. If plasma detectors pick up unusual ion compositions or unexpected particle populations, that could hint at exotic chemistry or even non-natural materials outgassing from the nucleus. Conversely, if the spacecraft see nothing unusual, if their data shows a comet that looks chemically and physically normal. Then we'd have to reconsider whether the ground-based anomalies are misinterpretations or measurement errors. There's a predicted opportunity that excites plasma physicists in particular. The comet's ion tail, that stream of charged particles stripped away by the solar wind, will cross paths with one or both spacecraft. When that happens, instruments designed to measure the local space environment will suddenly find themselves immersed in comet-derived plasma. They'll detect ions of whatever molecules are being ionized in the coma. Water ions, carbon monoxide ions, carbon dioxide ions, and, yes, metal ions like nickel and iron if they're present in sufficient quantities. The mass spectrometers aboard these missions can distinguish between different ions based on their mass-to-charge ratios, giving us a direct measurement of what's actually in the tail knot. Just what we infer from spectroscopy, magnetic field. Measurements offer another diagnostic. When the solar wind encounters a comet, the interplanetary magnetic field gets draped around the obstacle, creating a characteristic pattern. The shape and strength of this draping depend on the comet's outgassing rate, the composition of the coma, and how efficiently ions are created and interact with the field. Deviations from the expected pattern could indicate unusual plasma physics or unexpected conductivity, which in turn might point to exotic chemistry or material properties. But let's be realistic about the limitations. These spacecraft are not conducting dedicated comet flybys. They're on tight schedules with primary mission objectives that don't involve 3I Atlas. Hera needs to reach Dimorphos and carry out its survey. Europa Clipper needs to conserve power and momentum for its arrival at Jupiter. Pointing instruments at the comet requires fuel for attitude adjustments, competes with other observations, and risks missing planned activities. The distances involved, mean resolution will be limited. We're not going to get detailed surface maps or close-ups of active vents. We're getting contextual data, compositional hints, and environmental measurements. There's also the timing challenge. The flybys happen over spans of days, and the comet is moving, changing, potentially varying activity due to that 4-hour pulse or other factors. Coordinating observations, ensuring instruments are pointed correctly, and capturing data at optimal times requires careful planning and a bit of luck. Mission planners are doing their best, but they're working with constraints and uncertainties. Historically, opportunities like this have been hit or miss. When Oumuamua, the first confirmed interstellar object, tumbled through our solar system in 2017, we had no spacecraft in position to observe it closely. Everything we know came from telescopes on Earth and in Earth orbit, and it wasn't enough to definitively resolve the debates about its nature. By the time we realized how strange it had already passed perihelion and was fading from view. We didn't get a second chance. Comet Borisov, the second confirmed interstellar visitor, arrived in 2019 and gave us more time to study it. But again, no spacecraft encounters, just remote observations. 3 Atlas is our third confirmed interstellar object, and for the first time we have spacecraft close enough to potentially add insight-to measurements to the remote observations. It's not the comprehensive mission we'd design if we had years to prepare, but it's infinitely better than nothing. What Hera and Europa Clipper detector failed to detect will be cited in papers for years. It will inform models, settle or intensify debates, and guide how we interpret future interstellar visitors. The next few days will tell us whether the anomalies are robust and reproducible across different measurement techniques. If the spacecraft data aligns with the ground-based oddities, confidence in the reality of those oddities will skyrocket. If the spacecraft data contradicts or fails to see what telescopes have reported, then we'll have a calibration problem or a modeling issue to resolve. Either outcome is scientifically valuable. Either outcome moves us closer to understanding what 3i Atlas actually is. But while we wait for those flyby results, there's more to the story than just this one object. The anomalies don't stop at the sunward jet or the nickel chemistry or the rhythmic pulse. When you start cataloging everything strange about 3i Atlas, when you line up all the observations that don't quite fit, you realize this object is an embarrassment of riches for anomaly hunters. It's not just one or two oddities. It's 15, maybe more, rich, demanding explanation, each adding weight to the sense that we're missing something fundamental. Let's assemble the dossier. Imagine we're building a forensic file, compiling every piece of evidence that makes 3i Atlas unusual compared to what we expect from a typical comet. Some of these anomalies might have natural explanations when considered individually. Some might be observational quirks or measurement uncertainties, but taken together, they paint a picture of an object that refuses to conform to our models. Anomaly 1 is the absence of a long, sweeping tail. Most comets, especially when active and relatively close to the Sun, sport prominent tails stretching millions of kilometers. Dust tails curve gently following the comet's orbit. Ion tails stream straight back, pushed by the solar wind. 3i Atlas has a coma, yes, but the tail structures are muted, shorter, less dramatic than you'd predict based on its brightness and activity level. It's as if the material leaving the nucleus isn't being efficiently swept into a tail, or the production rate is lower than the coma brightness suggests. Anomaly 2 is the sunward jet we've already discussed in detail. Material streaming toward the Sun in defiance of radiation pressure and solar wind represents a fundamental violation of standard cometary behavior. This alone would make the object noteworthy. Anomaly 3 is the high nickel-tellurion ratio also covered earlier. Extreme metal abundance ratios don't fit solar or interstellar composition norms without invoking exotic formation environments or unusual chemistry. Anomaly 4 is the carbon dioxide-dominated coma. Most comets are water-rich. 3i Atlas flips that script with outweighing water by a factor of 8. This suggests formation in a cold, carbon-rich environment, possibly around a different type of star or in a molecular cloud with chemistry distinct from our solar system's birthplace. Anomaly 5 is the suppressed water relative to carbon dioxide. This isn't just restating Anomaly 4, it's highlighting that water, usually the dominant ice in comets, seems unusually depleted or locked away in this object. That has implications for where and how it formed and what its thermal history has been. Anomaly 6 is the rhythmic periodic outbursts, the 4-hour and possibly 2-hour cycles we discussed. Regular activity patterns hint at organized internal structure or specific geometric effects tied to rotation. Anomaly 7 is the asymmetric coma. Cometary comas are often asymmetric to some degree, but 3i Atlas shows pronounced asymmetries that don't align neatly with expected dust and gas distribution models. The sunward jet contributes to this. But even accounting for that, the overall coma shape is odd. Anomaly 8 involves non-random orientation changes. Some observers reported that the direction of plumes or jets shifted over time in ways that didn't obviously correlate with orbital mechanics or expected rotation effects. This is a subtler anomaly, harder to pin down, but it adds to the sense that the object's activity isn't following a simple script. Anomaly 9 is the extreme negative polarization signature. Polarimetry measures how light from an object is polarized, and comets typically show certain polarization characteristics based on their dust properties. 3I Atlas exhibited a deep negative polarization branch, meaning at certain scattering angles, the light was polarized in a direction opposite to what's typical. This suggests unusual dust grain properties, perhaps a different size, distribution, composition, or shape than solar system comets. Anomaly 10 is the anti-tail or narrow jet extension toward the Sun seen in earlier Hubble images. Before the dramatic TD image, Hubble captured hints of a narrow structure pointing sunward. At the time, it might have been dismissed as noise or a faint dust trail. In hindsight, it looks like an early warning of Anomaly 2. Anomaly 11 is the early water and hydroxyl outgassing far from the Sun. Observers detected water and O emissions when the comet was still several astronomical units out farther than you'd typically expect significant water ice sublimation. This fire hose of early activity suggests either that the surface ice is unusually exposed and volatile rich, or that some heat source beyond simple solar irradiation is driving sublimation. Anomaly 12 is the green color shift during a lunar eclipse. Comets can appear greenish due to emission from carbon-bearing molecules like C. But 3I Atlas showed a green hue even though spectroscopy indicated low C abundance. The color shift happened during a lunar eclipse when Earth's shadow affected the comet's illumination geometry, suggesting something about the scattering or emission properties changed in unexpected ways. Anomaly 13 is the detection of hydrogen cyanide emission. HCN was detected at a heliocentric distance of about 2.13 astronomical units. Interestingly, the HCN-2CN ratio was similar to solar system comets, suggesting that at least some chemistry is normal. But the presence of cyanide compounds adds another layer to the already complex chemical inventory, especially when you consider how nickel cyanide chemistry is used in industrial processes here on Earth. Anomaly 14 is the rapid change of the nickel-to-iron ratio with heliocentric distance. Iron emission appeared only when the comet crossed inside about 2.64 astronomical units from the Sun. Before that threshold, nickel dominated without significant iron. After crossing it, iron became detectable. This temperature-dependent release pattern suggests layered composition or distinct volatile reservoirs sublimating at different thresholds. But the sharpness of the transition is unusual. Anomaly 15 involves the delayed or withheld release of imagery from Mars orbiters. 3I Atlas passed relatively close to Mars about 29 million kilometers around October. Third, spacecraft like the ExoMars Trace Gas Orbiter and Mars Express have imaging capabilities that could have captured the comet. Yet public release of such imagery has been slow or absent. the high-resolution imaging science experiment ERISE aboard. NASA's Mars Reconnaissance Orbiter could have imaged the comet as well. The delay might be purely bureaucratic, a matter of data processing time or mission priorities, but it adds to the atmosphere of mystery. The sense that perhaps something in those images is being carefully reviewed before release. Each of these anomalies, considered in isolation, might be explained away. Unusual dust properties, exotic formation environment, observational artifacts, data processing delays. But when you stack 15 anomalies, when you see pattern after pattern that doesn't fit, you start to wonder whether the standard comet model is simply inadequate for interstellar visitors. Maybe objects formed around other stars bathed in different radiation environments, composed of ices and dusts with different primordial chemistry just behave differently. Maybe the rules we've derived from studying comets, born in our own solar system, don't apply cleanly to travelers from the galaxy at large. Or maybe, just maybe, we're looking at something that isn't entirely natural. That's the whisper in the back of the room. The speculation that no one wants to voice too loudly because it sounds like fringe science or tabloid fodder, but the whisper persists because the data keeps piling up in uncomfortable ways. Nickel without iron, cyanide compounds, rhythmic pulses, sunward jets. It's not that any single one of these screams artificial. It's that together they form a constellation of oddities that makes you question assumptions. So let's entertain that speculation directly, not as a conclusion, but as a thought experiment. What if some component of 3i Atlas, whether a coating, a structural element, or a deliberate payload, involves engineered materials? What would we expect to see, and does it match what we're observing? One of the wildest hypotheses circulating in the margins of the scientific discussion is this: parts of 3i Atlas may be engineered, not the entire object necessarily. Perhaps just a shell, a layer, or a component embedded within or attached to what is otherwise a natural comet nucleus. This idea sounds like science fiction, and it probably is. But let's follow the logic and see where it leads. Human technology makes extensive use of nickel alloys. Stainless steel, the ubiquitous, corrosion-resistant. Metal found in everything from kitchen sinks to spacecraft components. Components contains chromium and nickel. Superalloys used in jet engines and rocket nozzles. Materials that must withstand extreme temperatures and corrosive environments are often nickel-based, Inconel, alloy. These are trade names for nickel alloys prized for their strength and durability. If an advanced civilization wanted to build a probe or instrument package designed to survive millions of years, drifting through interstellar space exposed to cosmic rays, micrometeor impacts, and the corrosive effects of trace gases, nickel alloys would be a reasonable choice. Nickel cyanide chemistry is used in electroplating, a process where a thin layer of nickel is deposited onto another metal for protection or aesthetic purposes. The chemistry involves cyanide ions, which bind to nickel and help control the deposition process. If you were coating a structure with nickel for durability, you'd be working with nickel cyanide baths. Over time, especially under the harsh conditions of space, such coatings might degrade. Ultraviolet radiation, thermal cycling, abrasion, all of these could slowly ablate a nickel-rich surface layer. As that layer breaks down, it would release nickel atoms and potentially cyanide compounds into the surrounding space. Now, imagine this hypothetical nickel-coated structure embedded in or attached to a comet nucleus. As the comet approaches the sun and heats up, the surrounding ice sublimates, releasing gas and dust. The structure, if it's partially exposed, also heats up. Any remaining volatile compounds, any degraded surface materials begin to outgas. You'd see emissions of nickel, possibly cyanide species, and depending on the detailed chemistry, various carbon-bearing molecules. The ratios wouldn't match normal cometary material, because you're not just seeing sublimated ice, you're seeing the breakdown products of engineered materials mixed in with the natural outgassing. This scenario could explain the high nickel-tellurant ratio if the engineered component used a nickel-rich alloy with minimal iron. It could explain the hydrogen cyanide detections if cyanide chemistry was involved in the material's production or surface treatment. It could even explain the carbon dioxide dominance if the structure included carbon-based components, polymers, or organic coatings that break down into co under ultraviolet irradiation and heating. The rhythmic 4-hour pulse might make more sense in this context too, if the engineered component has vents, valves, or structural features that regulate gas flow either by design or as a consequence of how it's degrading. You could get periodic releases. Imagine a compartment that fills with sublimated gas from surrounding ice, builds pressure, and then vents through a crack or opening. Once vented, the pressure drops, the filling process starts again, and the cycle repeats. 4 hours would be the characteristic timescale for this particular system, determined by the size of the compartment, the sublimation rate, and the flow resistance of the vent. The sunward jet becomes less mysterious if it's driven by something other than random. Sublimation. Suppose the engineered structure has a directional vent nozzle or opening that happens to point sunward, based on how the object is tumbling or oriented. Gas escaping through that vent would create a jet in that direction regardless of where the sun is. It wouldn't be fighting radiation pressure so much as bypassing the usual mechanisms by releasing from a specific point, with enough force to overcome solar wind effects locally. This all sounds disturbingly plausible once you start down the path, but we have to be brutally honest about what this hypothesis requires. It requires that an advanced civilization built a probe or object, that this object ended up in interstellar space, that it happened to pass through our solar system, and that it just happens to have undergone enough degradation to release detectable signatures without being obviously artificial in structure. That's a lot of coincidences. It also requires that we're misinterpreting or overlooking natural explanations that could account for the same observations. The scientific community has a term for this kind of speculation. The extraordinary claims require extraordinary evidence principle, often attributed to Carl Sagan. The idea is simple. The more unusual and paradigm-shifting a claim is, the higher the burden of proof. Claiming that 3I Atlas has unusual chemistry is a modest claim requiring modest evidence. Claiming it's partially artificial is an extraordinary claim requiring extraordinary evidence. Do we have that level of evidence? No. We have intriguing anomalies, suggestive patterns, and a lack of fully satisfying natural explanations. That's not the same as proof of artificiality. Natural mechanisms can surprise us. The universe is creative. Chemistry under exotic conditions can produce unexpected results. Interstellar environments are not well sampled. We've studied solar system comets extensively, but those comets all formed in the same protoplanetary disk from the same starting materials under similar conditions. An interstellar comet formed around a different star in a molecular cloud with different metallicity, irradiated by a different spectrum of starlight, might just be weird without being artificial. It might teach us that normal comet chemistry is more diverse than we thought. But let's not dismiss the speculation entirely. Science advances by considering possibilities, testing them, and either confirming or ruling them out. The engineered alloy hypothesis is testable, at least in principle. If the spacecraft flybys detect particles or ions with isotopic ratios inconsistent with natural nucleosynthesis, that would be a smoking gun. If imaging reveals geometric structures, straight edges, or regular patterns that don't occur in natural rubble piles, that would be compelling. If spectroscopy finds molecules that only exist in industrial processes and have no plausible natural formation pathway, we'd have to take the idea seriously. Conversely, if future observations find natural mechanisms that explain the nickel dominance, the carbon dioxide excess, and the sunward jet without invoking engineered materials, then the hypothesis collapses under Occam's razor. The simpler explanation wins. We're not there yet. We're in the uncomfortable in-between zone where the data is weird enough to make you think, but not definitive enough to conclude. What makes this moment particularly fascinating is that we're not just speculating in a vacuum. We're on the verge of getting new data. The flyby results will either strengthen or weaken the case for exotic explanations. But even as we wait for that data, there's another layer to this story and another angle that makes the mystery deeper. Sometimes what you don't see is as important as what you do see. And in the case of 3I Atlas, there are missing pieces, withheld images, and unexplained delays that add an uncomfortable layer of intrigue. Sometimes what's hidden speaks as loud as what's shown. In the age of instant information, where astronomical discoveries are tweeted within hours, and preprint servers overflow with fresh papers, the absence of expected data becomes its own kind of signal. 3I Atlas passed relatively near Mars in early October, close enough that multiple Mars orbiters should have had excellent views of the comet. Yet the public release of imagery from those orbiters has been conspicuously slow, and in some cases apparently absent. The ExoMars Trace Gas Orbiter, a European Space Agency mission designed to study the Martian atmosphere, carries cameras capable of imaging objects in space. Mars Express, another ESA orbiter that's been circling Mars since 2003, has imaging capabilities as well. NASA's Mars Reconnaissance Orbiter hosts the high-resolution imaging science experiment HARASI, a camera so powerful it can resolve features less than a meter across on the Martian surface. When pointed at a comet millions of kilometers away, HARASI wouldn't achieve surface-level resolution, but it could certainly capture the coma structure, jet features, and overall morphology with far better clarity than most ground-based telescopes. 3I Atlas reached its closest approach to Mars around October 3rd at a distance of roughly 29 million kilometers. That's not a close flyby by any means, but it's well within imaging range for spacecraft instruments. The opportunity was there. The question is whether those instruments were actually pointed at the comet. And if they were, why haven't we seen the results? There are perfectly mundane explanations for delayed data release. Spacecraft data goes through processing pipelines. Raw images need calibration, correction for instrument artifacts, and validation before being released to the public or even to the broader scientific community. Mission teams have priorities. Mars orbiters are there to study Mars, not to conduct opportunistic comet observations, taking time away from primary mission objectives to image a passing comet requires justification, scheduling, and sometimes negotiation between different science teams. It's possible that the observations were low priority done if convenient, but not essential, and the data simply hasn't been processed yet because other tasks took precedence. There's also the reality of observing geometry. Just because a comet passes near Mars doesn't guarantee that orbiters in Martian orbit can easily point at it. Orbital mechanics, communication windows with Earth, spacecraft orientation, constraints, all of these factors limit what's actually feasible. Perhaps the Mars orbiters weren't in the right position or weren't configured to observe the comet effectively. Perhaps they tried but encountered technical issues, or well, not weather in the Earth's sense, but dust storms on Mars can affect surface-based observations, though they wouldn't affect spacecraft cameras in orbit. But let's consider the less mundane possibilities. What if the images exist, have been processed, and are being withheld pending further analyses? What if something in those images is unusual enough that mission teams want to triple-check their interpretations before releasing potentially controversial data? Space agencies are cautious institutions. They've been burned before by releasing data that was later reinterpreted or corrected, leading to public embarrassment and erosion of trust. If IRISI or TGO captured something unexpected in the inner coma of 3I Atlas, something that doesn't fit standard models, the instinct would be to verify thoroughly before publication. There's historical precedent for this kind of caution. When unusual features are detected, when anomalies appear that might challenge established science or generate sensational headlines, the data undergoes extra scrutiny. Review boards convene. Alternative explanations are exhaustively explored only when the team is confident that they understand what they're seeing, or confident that they don't understand but have exhausted prosaic explanations. Does the data get released? This process can take months or even years. The delay could also be political or bureaucratic rather than scientific. Space agencies or government or intergovernmental entities subject to public relations, considerations, funding, pressures, and international cooperation agreements. If data from one mission impacts the interpretation of another mission or touches on sensitive topics, there might be coordination delays while different stakeholders align their messaging. This sounds cynical, and perhaps it is, but these organizations don't operate in a vacuum. They navigate complex landscapes of public perception, scientific integrity, and institutional interests. Some observers have speculated, perhaps unfairly, that if the Mars orbiter images showed clear evidence of artificial structure or unambiguous anomalies that would force a rethink of what 3I Atlas is, those images might be subject to deliberate withholding. The reasoning goes that extraordinary claims require extraordinary caution, and releasing such images prematurely could trigger a cascade of media hype, public confusion, and pressure on scientists to to provide answers they don't yet have. Better to withhold until a fuller picture emerges, until multiple lines of evidence converge, and a coherent narrative can be presented. This kind of speculation quickly slides into conspiracy theory territory, and we should be careful not to go there without evidence. There's no indication of a coordinated cover-up. There's no leaked memo or whistleblower suggesting that something astonishing is being hidden. What we have is an absence of expected data and a natural human tendency to fill information voids. With speculation, the absence might mean nothing, it might mean everything. We don't know yet. What makes this absence frustrating is that the Mars orbiter imagery could answer key questions. If the images show a perfectly normal-looking coma with no sunward jet or unusual features, that would cast doubt on the ground-based observations. If they show the sunward jet clearly from a different angle and with high resolution, that would confirm it beyond reasonable doubt. If they show structure in the inner coma, hints of symmetry or focused venting, that would guide our models. The data exists, presumably in some form. We're just waiting for it to emerge from the institutional machinery. But missing Mars imagery isn't the only odd coincidence swirling around. 3I Atlas, in the days surrounding the comet's perihelion and its most unusual behavior, other strange events were reported in the near-Earth and solar environment. Taken together, they form a pattern that might be pure coincidence or might hint at something more coordinated or causally connected happening in our cosmic neighborhood. What if 3I Atlas's oddities aren't isolated? What if they're part of a pattern? Between October 11th and October 14th, 2025, reports emerged of 4 distinct sun-grazing objects diving toward the sun. These objects, tracked by solar observatories, appear to originate from roughly the same general direction in the sky as 3I Atlas. They plunge toward our star, some apparently disintegrating, others vanishing into the solar glare. Sun-grazing comets aren't rare. The Kreutz family, a group of comets thought to be fragments of a larger progenitor that broke apart centuries ago, regularly sends members diving sunward. Solar observatories catalogued dozens of these doomed comets every year as they vaporize in the sun's intense heat. But the timing here is curious. 4 objects in 4 days, all from a similar direction, overlapping with the period when 3I Atlas was exhibiting its most unusual behavior and approaching its own perihelion. Coincidence? Probably. The sky is big and the volume of space near the sun is constantly being crossed by small bodies. Our improved observational capabilities, especially with space-based solar telescope SME, we're detecting more of these objects than ever before. Finding 4 in quick succession isn't statistically impossible or even particularly unlikely during active periods. Yet, the clustering nags at the imagination. Could these sun divers be related to 3I Atlas? Could they be fragments that broke off earlier in its trajectory, following slightly different orbits that converged on the sun around the same time? Cometary nuclei are fragile. Tidal forces, thermal stresses, and rotational instability can shatter them into multiple pieces. If 3I Atlas shed fragments months or years ago, those fragments might have orbits differing slightly from the main nucleus, leading them to arrive at perihelion at different times. We've seen this with other comets. Shoemaker-Levy 9 famously fragmented before its collision with Jupiter, creating a string of pearls that impacted over several days. Spectroscopic analysis of the sun-diving objects could test this hypothesis. If their composition matches three atlases' unusual chemistry, that would strengthen the connection. If they show normal cometary composition, they're probably unrelated. But obtaining detailed spectra of objects about to be incinerated by the sun is challenging. They're faint, fast-moving, and visible only briefly. Most sun-grazing detections come from coronagraphs devices that block the sun's disk to reveal the faint surroundings. Those images don't provide spectral information. Another odd event occurred during this period that caught public attention, though it's even harder to evaluate. During a SpaceX Starship launch, observers analyzing video of the spacecraft against the backdrop of the moon noted a bright point of light near the lunar glare. This point appeared to hover for several seconds, in a position that didn't correspond to any known satellite, star, or planet. Then it disappeared. The internet predictably erupted with speculation. Was it a genuine object? A spacecraft? A piece of debris? Or was it an optical artifact, a lens flare, a reflection within the camera optics? Lens flares are common in astrophotography, especially when bright objects like the moon are in the frame. Light can scatter within lenses, reflect off sensor surfaces, and create ghost images that appear as bright spots or streaks. Distinguishing between real objects and optical artifacts requires careful analysis of the original footage, understanding of the camera system, and ideally confirmation from multiple independent cameras. In this case, such analysis has been inconclusive or absent from public reporting. The bright point might be something real, but it's just as likely, if not more likely, to be a mundane artifact. What makes this event tangentially relevant to 3I Atlas is the timing. The Starship launch occurred in mid-October, overlapping with a period of heightened comet activity and the sun-diving objects. If you're inclined toward pattern seeking, you might wonder whether there's a connection. Could the bright point near the moon be related to whatever's causing the comet anomalies? Could there be some coordinated activity, some hidden phenomena affecting multiple objects in nearer space simultaneously? This is where we have to pump the brakes on speculation. Coincidences happen. Humans are pattern recognition machines, evolved to spot connections even when none exist, because false positives were less costly than false negatives in our ancestral environment. Seeing unrelated events and constructing narratives, linking them, is something our brains do automatically. It doesn't mean the connections are real. But let's entertain the idea for a moment, not as a serious hypothesis, but as a thought experiment. Suppose there was some cosmic event or pulse, some disruption in the interplanetary environment that affected multiple small bodies simultaneously. Perhaps a burst of high-energy particles from the sun, a coronal mass ejection with unusual properties, or a density wave in the interplanetary medium. Could such an event trigger outgassing in comets, destabilize orbits, or interact with dust and debris in ways that produce transient optical phenomena? The physics would be challenging to work out, but it's not impossible in principle. Coronal mass ejections are massive eruptions of plasma and magnetic field from the sun that travel through the solar system at high speed. When they impact Earth, they cause geomagnetic storms auroras, and disruptions to satellites and power grids. When they encounter comets, they can compress the coma, intensify the ion tail, and trigger outbursts. If a particularly strong or unusual CME occurred in early to mid-October, it could have affected 3I Atlas and potentially other bodies in interplanetary space. Solar observatories monitor the sun constantly for such events. A quick check of solar activity reports for October would reveal whether any significant CMEs or solar flares occurred during the relevant period. If so, there could be a natural explanation linking some of the observations. If not, we're back to coincidence as the most likely explanation. The sun-diving objects, the starship Bright Point, and 3I Atlas's behavior might simply be unrelated events that happen to cluster in time by chance, or they might be connected by some common cause we haven't identified. Without more data, we can't distinguish between these possibilities. What we can say is that October 2025 has been an unusually eventful month for near-Earth and solar system astronomy, and 3I Atlas sits at the center of that activity. The most anomalous and intensely studied object in the mix. But 3I Atlas isn't the first interstellar visitor to challenge our assumptions. It's part of a progression, a series of objects arriving from beyond our solar system, each breaking rules in its own way. To understand where 3I Atlas fits in the larger picture, we need to look back at its predecessors and ask whether there's a pattern emerging in how interstellar visitors behave. 3I Atlas may not be unique, but it may follow a pattern that's only now becoming visible. The pattern is one of reversal of objects that arrive from interstellar space and proceed to violate our expectations in fundamental ways. It started in October 2017 with 1I Oumuamua, the first confirmed interstellar object detected passing through our solar system. Oumuamua was strange from the start. It showed no visible coma, no tail, no obvious signs of outgassing despite passing close. Enough to the sun that any water eyes should have sublimated vigorously. It was classified as an asteroid based on that lack of activity. But its trajectory told a different story. As astronomers tracked Oumuamua's path, they noticed it was accelerating slightly away from the sun in a way that couldn't be explained. By gravity alone, something was pushing it. In comets, this kind of non-gravitational acceleration is common and well understood. Outgassing creates a rocket effectoterial jets off the sunward side, and the recoil nudges the nucleus in the opposite direction. But Oumuamua wasn't outgassing visibly. No coma, no jets, no detectable gas. Yet it accelerated as if it were. Explanations proliferated. Maybe it was outgassing, something very faint, hydrogen perhaps, that wouldn't produce a visible coma, but could still provide thrust. Maybe it was an unusually strong radiation pressure effect acting on a very thin, flat object shaped like a solar sail. Maybe it was solid hydrogen ice, exotic and fragile, sublimating invisibly. Each explanation had problems. Each required assumptions that stretched what we considered normal. And then there was the shape. Observations suggested it was extremely elongated, perhaps 10 times longer than it was wide, cigar-shaped, or maybe even pancake flat. No asteroid or comet in our solar system looked quite like that. The scientific community debated intensely. Most researchers favored natural explanations, exotic as they were, but a few, most prominently astronomer Avi Loeb from Harvard suggested that Oumuamua's properties were consistent with artificial origin, perhaps a light sail or probe from an alien civilization. That suggestion was controversial, to put it mildly. Most astronomers found it premature and insufficiently supported by the data. But the idea entered public consciousness and refused to leave. Oumuamua became not just a scientific puzzle, but a cultural touchstone for the question of whether we're alone in the universe. Then, in August 2019, amateur astronomer Gennady Borisov discovered 2I Borisov, the second confirmed interstellar object. This one looked much more like a normal comet. It had a clear coma, showed vigorous outgassing, contained familiar molecules like water and carbon monoxide in expected ratios. Its behavior was comforting in its normalcy. See, researchers said, interstellar visitors can be ordinary. Borisov proved that not every object from beyond our solar system needs to break the rules. It was a comet, it acted like a comet, and while its interstellar origin was extraordinary, its nature was reassuringly familiar. But now we have 3I Atlas, and the strangeness is back with a vengeance. If Oumuamua was strange for what it didn't show, 3I Atlas is strange for what? It does show in the wrong places. A sunward jet where there should be an anti-solar tail. Nickel without iron. Carbon dioxide drowning out water. Rhythmic pulses like a mechanical heartbeat. This object isn't failing to behave like a comet. It's behaving like a comet that read the textbook backwards. When you line up these 3 visitors in chronological order, a pattern emerges. First, an object with no activity where there should be activity, but mysterious acceleration. Second, an object with normal activity and reassuring chemistry. Third, an object with reversed activity and bizarre chemistry. It's as if the universe is testing us, presenting a progression of anomalies to see how we respond. Or perhaps it's teaching us that our categories of comet, asteroid, and interstellar visitor are too rigid to base on a sample size of one solar system. The key question is whether these objects are outliers or harbingers. Are they rare exceptions, statistical flukes that grab our attention precisely because they're unusual, while hundreds of normal interstellar objects pass unnoticed because they're too faint or too ordinary to detect? Or are they the first representatives of a much larger population of weird things drifting through the galaxy, objects formed under conditions so different from our solar systems that they naturally violate our expectations? The answer has profound implications. If most interstellar visitors are strange, then our solar systems, comets, and asteroids might be the outliers, products of one particular set of formation conditions that aren't representative of the galaxy as a whole. We'd need to broaden our models, incorporate a much wider range of chemical and physical possibilities, and accept that what we call normal is just local normal, not universal normal. If most interstellar visitors are ordinary and we're just noticing the weird ones because they're noticeable, okay, then Oumuamua and 3I Atlas are curiosities, interesting, but not paradigm shifting. They're the astronomical equivalent of 2-edit, calves are rare birth defects or unusual circumstances that don't reflect the broader population. We'd still want to understand them, but we wouldn't use them to rewrite our textbooks. The reversal motif, this tendency for interstellar objects to flip expectations, might be telling us something deeper about the galaxy's diversity. Star formation happens in a variety of environments. Some stars form in dense clusters where radiation and gravitational interactions are intense. Some form in isolation in the sparse outer regions of molecular clouds. The composition of the gas and dust varies depending on the metallicity of the region. The history of previous supernova enriching the material and the presence of nearby massive stars. Comets forming around a star in a metal-rich region might have different chemistry than those forming in a metal-poor region. Comets forming close to massive stars might be radiated more intensely, altering their surface properties or driving off certain volatiles, preferentially 3I Atlas, with its carbon dioxide dominance and metal anomalies, could be a product of such an exotic birthplace. Maybe it formed around a carbon star type of star where carbon is more abundant than oxygen in the outer atmosphere, leading to carbon-rich dust and chemistry. Maybe it spent time in a dense molecular cloud where cosmic rays processed the ices in unusual ways. Maybe it's old, billions of years old, and its surface has been altered by prolonged exposure to the interstellar radiation field. All of these are natural explanations that could account for oddities without invoking artificiality. But the reversal motif also resonates with a more speculative interpretation. If interstellar space is occasionally traversed by probes or artifacts from other civilizations, those objects would naturally violate our expectations because they weren't designed by natural processes. They'd have materials chosen for engineering reasons, not cosmic abundance. They'd have structures optimized for function, not random accretion. They'd potentially have systems that operate rhythmically or directionally because they were built to do so. In that framework, the reversal isn't a coincidence, it's a signature. Objects that break the rules might be breaking them because they were made by rule breakers. This brings us to a critical juncture. 3I Atlas, Oumuamua, and potentially future interstellar visitors are pushing us to expand our thinking. Whether the explanation is exotic natural processes or something more radical, we're being forced to confront the limits of our models. And as we grapple with these cosmic puzzles, it's worth noting that 2025 has been a year of paradigm-challenging discoveries across multiple fields of science. 3I Atlas isn't happening in isolation. It's happening in a year when other fundamental assumptions are being tested, when dark stars are confusing cosmologists, when AI is discovering patterns in physics that humans missed, when quantum teleportation is achieving milestones that seemed impossible decades ago, and when fusion energy is crossing thresholds that promise to reshape civilization. Maybe we're entering a period where anomalies are the norm, where the universe is revealing complexities we hadn't anticipated across every scale we study. Recent results from the James Webb Space Telescope and other surveys have thrown cosmology into an unexpected debate about the formation sequence of the universe's first structures. The Standard Model holds that galaxies formed first, growing from small density fluctuations in the early universe, and then black holes formed at their centers as matter accumulated and collapsed. This sequence made sense. Gas condenses into stars, stars cluster into galaxies, and eventually enough mass concentrates in galactic cores to form supermassive black holes. It's a bottom-up process, building complexity from simple beginnings. The JWST keeps finding black holes that seem too big, two early supermassive black holes millions to billions of times the mass of our Sun, existing when the universe was less than 1 billion years old. That's not enough time for them to grow. Through the standard process of accretion and mergers, either these black holes started much bigger than theory predicts, or they grew much faster, or the sequence is wrong. Maybe black holes formed first before galaxies seeding the structures that would later become galactic centers. This possibility has led to the concept of dark stars. Hypothetical early objects powered not by nuclear fusion like normal stars, but by the annihilation of dark matter particles. If dark matter accumulated in dense clumps in the early universe and began annihilating, it could release energy that would heat surrounding gas and make it glow. These dark stars could be enormous, far larger than any fusion-powered star, and they could eventually collapse into black holes that would then serve as seeds for galaxy formation. It's a reversal of the expected order: black holes before galaxies instead of galaxies before black holes. The evidence isn't definitive yet. The observations pushing this debate are at the edge of JWST's capabilities, and alternative explanations exist. Maybe the black holes aren't as massive as they appear. Maybe they're accreting at higher rates than we thought possible. Maybe our models of early universe conditions need refinement. But the fact that we're even having this conversation, that the standard cosmological sequence is being questioned based on hard observational data, reflects a broader theme. Our models are being tested and found wanting. The universe is more complex, more surprising than our neat frameworks anticipated. If we can be wrong about something as fundamental as the formation sequence of galaxies and black hole structures that define the large-scale architecture of the cosmos, then being wrong about the behavior of interstellar comets seems almost trivial by comparison. Both cases involve taking what we learned from limited samples and assuming it applies universally, only to find that the universe has tricks we didn't account for. The dark stars debate matters for our discussion of 3I Atlas because it establishes context. We're not in an era of settled science where all the big questions are answered and we're just filling in details. We're in an era where fundamental assumptions are being challenged across multiple domains. That doesn't mean every anomaly is revolutionary. Most anomalies turn out to be measurement errors, calibration issues, or previously known effects in unfamiliar guises. But some anomalies are real, and some of those real anomalies force us to rebuild our theories from the ground up. THREEI. Atlas might be one of those theory-breaking anomalies, or it might be a lesson in exotic but natural cosmic chemistry. The point is, we can't dismiss it just because it doesn't fit our modelers, because our modelers are demonstrably incomplete. The universe is under no obligation to conform to our expectations, and 2025 is teaching us that lesson repeatedly. In 2025, artificial intelligence is no longer just assisting scientists, it's discovering things humans missed. Machine learning algorithms trained on vast data sets are identifying patterns, correlations, and anomalies that would take human researchers years to find, if they found them at all. This is transforming every field it touches, and astrophysics is no exception. Recent papers in high-energy physics and cosmology have listed AI systems as co-authors, acknowledging that the algorithms contributed substantively to the discovery process. These aren't just data processing tools. They're hypothesis generators, pattern recognizers, operating in high-dimensional spaces where human intuition struggles. An AI trained on galaxy spectra can spot unusual emission lines in thousands of objects simultaneously. An AI analyzing light curves from variable stars can detect periodicities buried in noise that visual inspection would miss. This capability has profound implications for studying objects like 3I Atlas. The data we have, spectra, images, light curves, contains far more information than any single human researcher can fully extract. There are correlations between chemical abundances and activity patterns, subtle timing relationships, spatial structures in the coma that might reveal internal organization. An AI specifically trained on cometary data and then turned loose on 3I Atlas might identify patterns that explain the anomalies or flag additional oddities we haven't noticed. But this power comes with risks. AI systems can hallucinate patterns in noise. They can overfit to training data, learning the quirks of specific instruments rather than true physical relationships. They can encode biases present in their training sets, reinforcing assumptions rather than challenging them. An AI trained primarily on solar system comets might flag everything about 3I Atlas as anomalous simply because it's different, not because it's physically impossible. The key is combining AI's pattern recognition with human skepticism and physical intuition. Let the AI scan for oddities, but demand that humans verify them, check for artifacts, and construct physical models to explain them. This hybrid approach is already being used in gravitational wave astronomy, where AI flags potential signals in detector noise, and human experts evaluate whether they're real events or glitches. The same approach could revolutionize how we study interstellar visitors. Imagine an AI system that ingests every observation of 3I Atlas, every spectrum, every image, every timing measurement, and looks for correlations. It might discover that the 4-hour pulse correlates with specific spectral line strengths, suggesting a chemical cycle. It might find that the sunward jet's intensity varies with the nickel-to-iron ratio, hinting at a shared driving mechanism. It might identify precursor signals, subtle changes in the coma hours before outbursts that could predict future activity. Or it might find nothing, confirming that the anomalies are genuinely random or driven by processes too complex or chaotic for pattern recognition. That outcome would also be valuable. It would tell us we're not missing obvious connections, that the mystery is genuinely mysterious. The broader point is that 2025 represents a threshold in how we do science. We're augmenting human intelligence with machine intelligence in ways that are qualitatively different from previous computational tools. This changes what's possible, what questions we can ask, and how quickly we can answer them. If 3I Atlas is hiding secrets in its data, AI might be the key to unlocking them. And if AI confirms that the anomalies are robust and interconnected, that will make the case for exotic explanations, natural or otherwise, significantly stronger. Information does not travel. It dies in one place and resurrects in another without ever crossing the space between. This sounds like magic, but in 2025, it is becoming routine. Researchers have just achieved something that would have seemed impossible a decade ago. they have successfully teleported quantum information across 56 kilometers of standard fiber optic cable, coexisting alongside ordinary internet traffic, the same cables that carry your emails and video streams. This is not theoretical. It happened. The breakthrough came from scientists at Northwestern University working with teams across multiple institutions, and their results demonstrated that quantum states could be transferred with greater than 90% accuracy over metropolitan distances, using equipment that integrates with existing infrastructure. Think about that for a moment. The same fiber that brings Netflix to your home, the same cables buried beneath city streets that carry banking transactions and medical records are now carrying quantum information. Reality itself, in its most fundamental form, is being transmitted alongside your morning news. The mechanism behind this operates on principles that should trouble anyone who believes space is merely empty void. Quantum entanglement creates a link between two particles, a connection so instantaneous that Einstein himself called it spooky action at a distance. Two particles become entangled, their properties forever bound. You measure one, and instantaneously the other responds, no matter if they are separated by kilometers or light years. The physicists doing this work carefully prepare pairs of entangled photons. One photon carries the quantum state they want to transfer. The other is waiting at the destination. The moment they perform a measurement on the first photon and the intermediary particle, that measurement forces the distant photon to collapse into the state of the original. The information is gone here. It exists there. No signal travels between them. No message passes through space. The correlation is instantaneous. Einstein hated this. He called it ghostly, unacceptable, a violation of everything physics should be. Yet here we are in 2025, harnessing that ghostliness. But here is where it gets crucial for understanding the implications. This process requires timing so precise that error correction becomes a complex dance. Every entangled photon travels through fiber, and fiber is hostile to delicate quantum states. Thermal noise, vibrations, electromagnetic interference, all these threaten to decohere the quantum information before it arrives. The researchers solve this using advanced filtering techniques, superconducting detectors cooled to temperatures just above absolute zero, and active feed-forward protocols where classical information about measurement results travels alongside the quantum signal. The classical information tells the receiver how to manipulate the quantum state to restore it perfectly. It is like sending both a message and the key to decode it simultaneously. Except the key itself is quantum and must be protected with extraordinary care. The distances involved are not vast by cosmic standards, but they are vast by the standards of quantum systems. 56 kilometers is an enormous distance to maintain quantum coherence. The fact that this is now repeatable, that it can be done over and over with consistent results, marks a transition from laboratory curiosity to practical technology. The implications for deep space communication are staggering. Imagine probes exploring the outer solar system or eventually interstellar space. Normal radio signals degrade over distance, require enormous power, travel at light speed, and take hours to cross the solar system. A transmission to Mars takes between 4 and 24 minutes, depending on orbital positions. A message to the Voyager. Probes takes 18 hours to reach them. This is not because the signals are weak, but because light itself moves at a finite speed. A quantum communication link would establish a secure channel where any eavesdropping attempt instantly destroys the signal, alerting both parties to intrusion. The security is absolute, not through encryption, but through the laws of physics themselves. More importantly, quantum communication could enable distributed quantum computing, where distant quantum processes collaborate on the same problem in real time without the lag that light speed imposes on classical communication. You cannot transmit faster than light, but quantum entanglement allows you to coordinate in ways that appear to the observer almost instantaneous. The universe grants us this gift, the ability to have particles separated by vast distances act as if they were one unified system. Here is where the analogy crystallizes. Imagine fiber optics as living blood vessels carrying information through space itself. Classical fiber optics carry pulses of light encoded with ones and zeros binary information. The digital language of modern computing. Quantum fiber optics would carry something more fundamental, the raw quantum possibility itself, like the difference between describing a landscape and standing in it, like the difference between reading sheet music and hearing the symphony. The information is not a message about reality. It is reality transferred intact from one location to another. Now consider the comet 3I Atlas. What if, in the distant future, humanity sends quantum-equipped probes to intercept objects like this? These probes would need instantaneous coordination, secure channels that cannot be intercepted, distributed processing power to analyze anomalies in real time. The mechanisms enabling that future technology are being tested today. We are building the infrastructure for cosmic communication networks without realizing it. This brings us to a darker speculation, one that connects the mechanics of quantum teleportation to the mysteries of 3I Atlas. If quantum communication becomes commonplace and enables advanced propulsion or exotic physics applications, could Atlas itself be using something similar? Not necessarily quantum teleportation as humans understand it, but a mechanism that exploits quantum phenomena to move matter or energy in unexpected ways. The rhythmic outbursts, the chemical composition that does not match models, the coherent jets that should not exist in a body so small, and icy, all of these hint at something. Manipulating the physics at scales where quantum effects become significant. Stars are mostly classical, planets are classical, but small bodies, especially those with complex internal structure, ice and organics, they operate in a regime where quantum phenomena could genuinely matter. Quantum tunneling could allow particles to move through barriers they should not be able to cross. Quantum fluctuations could drive processes we do not yet understand. Entanglement between subsystems could create correlations that appear impossible by classical standards. What if Atlas is not simply a comet? What if its behavior reflects an environment or process that operates partially in the quantum realm, where superposition and entanglement are not abstractions but mechanical realities? The very act of observing such an object, measuring it with telescopes and spectrographs, would disturb its quantum states, potentially explaining inconsistencies between different observations. changes in brightness and composition that seem to shift based on how we look at it. This is not madness. This is extension of known physics into unknown territory. The observer effect, that central pillar of quantum mechanics, tells us that measurement itself changes reality. When we observe 3I Atlas, we are not passively watching it, we are interacting with it. We are collapsing superpositions, fixing properties that might otherwise remain in a state of quantum uncertainty. 2025 is the year when we learned we could teleport quantum information through existing infrastructure. What remains to be seen is whether the cosmos has been doing something similar all along. Whether objects like 3I Atlas are cosmic quantum. Computers manipulating their own states through entanglement and superposition, appearing strange to us only because we are observing the collapse of possibilities into classical reality. The sun has been burning for 4.6 billion years, fusing hydrogen into helium, releasing more energy in a single second than humanity has used since the dawn of civilization. Every photon that warms your face, every ray of light that makes photosynthesis possible, every bit of energy that drives our weather and our oceans, all of it comes from fusion. Scientists have understood fusion for a century. What they could not do was repeat it on Earth in a controlled way that produced more energy than it consumed, that changed. On February 23, 2025, the National Ignition Facility in California achieved ignition for the 7th time in repeated experiments, setting a new record. They fired lasers carrying 2.05 megajoules of energy at a target, and the fusion reaction produced 5.0 megajoules, nearly 2.4 times the input energy applied directly to the target itself. More recently, on June 22, 2025, a collaborative team led by Los Alamos National Laboratory working with Lawrence Livermore achieved ignition again, producing 2.4 megajoules in a self-sustaining reactioner burning plasma that achieved critical conditions. 8.6 megajoules have been achieved in later experiments. The pattern is clear. Ignition is no longer a one-time accident. It is repeatable, it is scalable, it is becoming the baseline. How does fusion work? Two hydrogen atoms are pushed together with such force that their nuclei merge. The strong nuclear force overcomes electromagnetic repulsion. The new nucleus, helium's slightly lighter than the sum of its parts. That missing mass, by Einstein's equation, becomes energy. Enormous energy. The temperatures required to achieve this, millions of degrees, can only be sustained in two ways. Inertial confinement uses lasers so powerful they compress a tiny pellet in a fraction of a nanosecond, creating the densities and temperatures of stellar cores for microseconds. Imagine taking the entire core of the sun and compressing it into an object the size of a grain of sand. That is what happens inside the target chamber. Magnetic confinement uses electromagnetic fields to trap plasma, superheated, ionized gas in a container shaped like a donut, holding it stable for longer durations. The National Ignition Facility chose inertial confinement. 292 separate laser beams fire simultaneously at a cylinder called a hologram. Inside that cylinder sits a capsule filled with deuterium and tritium. The energy compresses it to 50 times. Normal density. Fusion ignites. Energy is released. The breakthrough is not just that ignition happens, it is that it is repeatable. It is becoming more efficient. In 2024, the facility achieved 120% energy gain on some shots. The trajectory is upward. Meanwhile, other groups are pursuing magnetic confinement. TE Technologies announced in April 2025 that their experiment, called Norman, has achieved their highest steady-state plasma performance using only neutral beam injection, without the complex quartz tube formation systems of earlier designs. This simplifies the apparatus dramatically. Think about what that means. Simpler apparatus means cheaper apparatus. Cheaper means scalable. Scalable means commercial. Commonwealth Fusion Systems, backed by over $2 billion in private capital, has completed assembly of magnetic confinement systems for their spark reactor, expected to demonstrate net energy generation in the early 2027 timeframe. Private capital flowing into fusion means the market believes fusion is coming. Business does not fund mirages. Business funds the future. This is the point of no return. We are transitioning from proving that fusion is possible in principle to demonstrating that fusion can be commercially viable in practice. We've entered a regime where energy sources start to behave in fundamentally new ways. Classical physics says energy density increases with difficulty, with cost, with environmental impact. Fossil fuels require extraction, processing, transportation, combustion, and they produce waste carbon and greenhouse gases that reshape the climate. Fission requires enormous safety infrastructure, cooling systems, waste storage, security protocols to prevent proliferation. But fusion exists in a different category. Two atoms merge. Helium forms. The ocean provides the fuel hydrogen isotopes dissolved in water. The waste is minimal. The energy release is absolute. Fusion does not produce carbon dioxide. It does not produce long-lived radioactive waste. It produces inert helium. It is the closest thing to magic that physics allows. Now draw a parallel. Just as fusion is challenging our foundational notions of what is possible in energy production, forcing us to rewrite economics and physics simultaneously, 3i Atlas is challenging our foundational notions of what is possible in small body. We thought we understood comets. We thought we understood what ice and rock could do under pressure and radiation. We had models tested and refined over decades. 3i Atlas is proving that comets can be far stranger than models predicted. The velocity, the composition, the outbursts. The jets, all of it suggests that either our models are incomplete or something unusual is present. And here is the unsettling thought. What if the universe is entering a period where anomalies across multiple scales are not exceptions, but signals that we are only beginning to read? Consider the timeline. In 2022, fusion ignition was achieved for the first time. In 2023, multi-node quantum teleportation networks were demonstrated. In 2024, quantum teleportation over existing internet infrastructure was successfully performed, proving the technology could scale beyond the laboratory. And in 2025, we see ignition repeated, refined, moving toward commercial viability. Simultaneously, in 2025, 3 Atlas exhibits behavior that contradicts established models. These are not connected events in any causal sense, but they are connected. They all suggest that the universe operates with greater flexibility than our current models allow. Energy can be released through fusion in ways we did not think was scalable. Information can be transferred through quantum channels. Alongside classical matter can behave in ways that suggest hidden complexity or unknown mechanisms. All of this in a single year. All of this converging. The implications compound. Fusion will soon provide clean, abundant energy. With that energy, we can build quantum networks on planetary scales. With quantum networks, we can coordinate distributed sensing, distributed computing, distributed control of technologies we cannot yet imagine. And if objects like 3I Atlas are revealing that nature operates with hidden layers of complexity, then every new quantum network we build, every fusion plant we activate, every sensor array we deploy might be tools for discovering what we have missed. We are not just building new technology, we're entering a new regime of physics. The universe is preparing to reveal secrets it has kept hidden for billions of years. The big question: are we entering a decade of rule-breaking discoveries? Reconsider everything. 3 Atlas arrived from interstellar space with a trajectory that suggested gravitational influence we cannot explain. The gravitational perturbations implied forces acting on the object that should not exist in the vicinity it was traveling. Its jet is continuous and coherent in a way that defies cometary models. Cometary outgassing should be chaotic, driven by localized heating, unpredictable in direction and intensity. Yet 3I Atlas produces a jet that looks engineered, precise, constant. Its composition shows materials that should not exist together under standard cometary formation scenarios. The chemistry does not match what we expect from objects formed in protoplanetary disks billions of years ago. Its brightness oscillates with rhythms that seem too regular to be accidental, too precise to be random. Its trajectory has drifted in ways that imply propulsion or momentum transferred beyond outgassing, beyond what physical processes we know can provide. These are not ambiguous observations. These are data points that falsify established models. They are not inconsistencies to be explained away or errors to be corrected. They are signals that something fundamental is different. Weave in the other. Discoveries of 2025. Dark stars are proposed objects where dark matter accumulates. Around primordial black holes, exotic objects that would completely alter our understanding of stellar populations in the early universe. If dark stars exist, the cosmos contains populations of objects we have never studied. Objects that may outnumber ordinary stars by factors of millions. Quantum teleportation is now a practical technology demonstrated across metropolitan distances with high fidelity, proving that the laws of quantum mechanics are far more exploitable than physics textbooks suggested. Fusion has moved from theoretical possibility to repeatable demonstration of net positive energy gain, proving that energy production can be decoupled from combustion and fission and placed in the regime of stellar processes. Artificial intelligence is beginning to identify patterns in datasets that human researchers miss, discovering relationships in physics that CONVENTIO and AL analysis overlooked. Machine learning algorithms trained on astronomical data are finding correlations that human eyes cannot see, anomalies that humans have been taught to filter out as noise. All of this points to a singular thesis. 2025 is not a year of incremental progress. It is the beginning of a paradigm shift. For 3 centuries, science has operated under the assumption that anomalies are errors, that models are approximately correct, that new observations refine existing frameworks rather than challenge them. This assumption worked well. It allowed us to understand gravity, electromagnetism, quantum mechanics, relativity. But what if that is wrong? What if anomalies are not noise, but signal? What if models are not approximately correct, but fundamentally incomplete? What if the universe is far stranger than our current categories allow, and we are only beginning to perceive the strangeness? What if we have been filtering out signals because we were trained to see them as noise? Think about what we call natural. A comet is natural ice and rock in space, ejected from a star system, drifting between worlds. Fusion is natural. It powers the sun, forges elements in stellar cores, one of the most fundamental processes in the universe. Quantum entanglement is natural, a demonstrated feature of quantum mechanics, tested and confirmed countless times. But 3i Atlas might be natural too if we expand our category of natural to include phenomena we do not yet understand. What if being natural no longer means conforming to our current models? What if being natural simply means existing without deliberate human intervention? By that definition, 3i Atlas is natural. It came from the stars. It is not artificial. It is not engineered by human hands, yet it behaves in ways that contradict everything we thought we knew about objects in space. The deeper question becomes, are we undercounting phenomena that do not fit neat categories? Astronomy catalogs objects as stars, planets, asteroids, comets, black holes, neutron stars, brown dwarfs, each a box with properties and behaviors. We put objects into categories and we study the categories. But what if there are objects that span multiple categories? What if there are processes that operate across scales we have not examined carefully enough? What if 3i Atlas is the first of many discoveries that will not fit existing boxes? What if the universe has been showing us these objects all along, and we simply did not have the tools to recognize them? Consider the cascade of implications. If dark stars exist, the universe contains populations of objects we have never studied with properties and behaviors completely unknown. We would need to rebuild our models of galactic structure, of stellar populations, of the early universe. If quantum teleportation can operate through existing infrastructure, secure quantum networks can be deployed globally, enabling technologies we cannot yet predict. Communication systems will be transformed, computing will be transformed, science itself will be transformed. If fusion achieves commercial viability, energy scarcity ends, and every technology limited by energy becomes possible. Climate change becomes solvable. The global economy transforms. Material science transforms. Space exploration becomes affordable and practical. If anomalies like 3i Atlas are not exceptions but representatives of a larger class of undiscovered phenomena, then our models are not complete by degrees but missing entire categories of physics. We are not just refining our understanding, we are discovering that the universe has dimensions we did not know existed. What will Hera reveal when it tracks 3i Atlas? What will the Europa Clipper spacecraft send back if it encounters this object or others like it in the deep solar system? These are not idle questions. They're about discovering what being natural means in a universe we're only beginning to understand. The data collected in the coming weeks could reshape our conception of comets, of propulsion, of what small bodies in space are actually capable of doing. It could reveal that 3I Atlas is a precursor to discovery of a new class of objects entirely. It could show that anomalies are not exceptions, but a signal that we have been modeling the cosmos with dangerous incompleteness. The universe may be trying to tell us that our maps are missing entire continents, our physics textbooks incomplete, our categories too narrow. Here is what must be understood. Every great discovery in history followed this pattern: an observation that did not fit the model, dismissal as error or anomaly, continued observation and measurement, realization that the model itself was wrong. Newton was wrong about gravity, but only slightly. Einstein corrected it. Maxwell understood electromagnetism, but quantum mechanics showed that light and matter were more entangled than classical physics allowed. Each generation discovers that the previous generation's models were incomplete. Ptolemy thought Earth was the center. Copernicus was right. Kepler refined the orbits. Newton explained the force. Einstein added space and time. Dirac predicted antimatter. 2025 may be the year when we discover that our current models of comets, energy, information, and the nature of the cosmos are not just incomplete, but missing entire dimensions of physics. The universe is not broken. Our understanding is. So, stay tuned, watch the data, scrutinize what Hera observes, monitor what interplanetary probes report, listen to what artificial intelligence discovers in the datasets we cannot manually analyze. The universe is about to tell us something we did not expect. It always does. 3I Atlas is just the first voice in a conversation that is about to get very loud. In the coming months, we will learn whether our models hold or whether reality is stranger, deeper, and far more wonderful than we ever imagined. The next chapter of physics is being written now. Pay attention. Let's zoom out for a moment and consider the bigger picture. The anomalies we're seeing with 3I Atlas don't exist in a vacuum. They're part of a broader pattern of scientific upheaval that's been building throughout 2025. This isn't just about one weird comet anymore. It's about a cascade of discoveries across multiple fields that are collectively challenging our understanding of reality itself. Think of it as a perfect storm of paradigm shifts, each one adding weight to the others, creating a momentum that's becoming impossible to ignore. In particle physics, researchers at the Large Hadron Collider have been detecting unexpected decay patterns in certain exotic particles that don't match the standard model's predictions. These aren't huge deviations, they're subtle, almost whispers in the data, but they're consistent across multiple independent experiments. The statistical significance is approaching the threshold where physicists can no longer dismiss them as statistical fluctuations. Meanwhile, in neuroscience, new imaging techniques have revealed neural networks operating in ways that defy our current understanding of brain function. Scientists are observing what appears to be quantum coherence in microtubule structures within neurons, suggesting that consciousness itself might involve quantum processes at a biological scale. This was once considered fringe science, but the evidence is becoming harder to ignore. In climate science, researchers are documenting feedback loops in Arctic permafrost melt that are accelerating faster than any model predicted. The chemistry of how methane releases from thawing ice is more complex than we thought, involving microbial processes that respond to temperature changes in non-linear ways. These discoveries aren't just academic curiosities. They're forcing us to reconsider everything from how we model climate change to how we approach potential mitigation strategies. Even in mathematics, there have been breakthroughs that suggest the foundations of how we understand numbers and relationships might need rethinking. A proof emerged this year showing that certain mathematical structures we thought were well understood actually contain hidden complexities that could ripple through everything from cryptography to theoretical physics. What connects all these seemingly disparate discoveries? They all point to a universe that's more interconnected, more complex, and more surprising than our current frameworks allow. They all suggest that the boundaries we've drawn between different fields of study might be artificial constructs that don't reflect how reality actually operates. And they all imply that the reductionist approach that has served science so well for centuries might be reaching its limits. The reductionist method breaks complex systems into their constituent parts to understand how they work. It's given us everything from Newton's laws to the periodic table to the genetic code. But what if some phenomena can only be understood holistically? What if the interactions between parts create properties that don't exist in the parts themselves? This is where 3i Atlas becomes particularly interesting. Its anomalies span multiple domains: physics, chemistry, dynamics, even potentially information processing. A purely reductionist approach might explain one or two of its oddities, but it struggles to account for the entire package. What if we need a new kind of science, one that embraces complexity, that looks for patterns across scales, that's comfortable with uncertainty and paradox? Some researchers are already calling this complexity science or integrative science, but whatever name we give it, the need is becoming clear. The universe isn't handing us neatly packaged problems anymore. It's presenting us with systems where everything affects everything else, where cause and effect become tangled, where simple models fail to capture the richness of reality. This doesn't mean we should abandon our current scientific methods. The rigor, the skepticism, the demand for evidence, these remain essential. But perhaps we need to supplement them with new tools, new perspectives, new ways of seeing. The AI systems we discussed earlier might be part of this solution. They can detect patterns that span multiple data sets, that connect observations across different fields, that suggest relationships human researchers might miss due to disciplinary boundaries. But AI alone isn't enough. We need human creativity, intuition, and the willingness to entertain seemingly wild ideas while still maintaining scientific rigor. We need to foster collaboration between fields that rarely talk to each other: astronomers working with quantum physicists, climate scientists collaborating with neuroscientists, mathematicians partnering with biologists. Most importantly, we need intellectual humility, the recognition that despite all our knowledge, we're still just scratching the surface of understanding reality. 3i Atlas, with its collection of anomalies, is like a mirror reflecting back to us the limits of our current knowledge. Every time we think we've figured out one piece of the puzzle, another piece emerges that doesn't fit. This isn't frustrating, it's exciting. It means there's still so much to discover, so many mysteries waiting to be unraveled. The coming weeks and months will be crucial. As data from the spacecraft flybys comes in, as AI systems analyze the growing data set, as researchers around the world apply their collective brainpower to these puzzles, we'll start to see whether we're on the verge of a scientific revolution, or whether these anomalies will eventually be explained within existing frameworks. Either way, we learn something valuable. If it's a revolution, we get to witness one of those rare moments in human history when our understanding of reality undergoes a fundamental shift. If it's not, we still deepen our knowledge and refine our models. The real danger isn't being wronged, it's being complacent, assuming we've figured things out when there's still so much to learn. 3i Atlas is teaching us that lesson in the most dramatic way possible, by presenting us with an object that refuses to conform to our expectations, that challenges us to think bigger, to question assumptions we didn't even realize we were making. That's the true value of anomalies. They're not just puzzles to be solved, but invitations to expand our understanding, to see the universe with fresh eyes, to recognize that reality is stranger and more wonderful than we can currently imagine. Let's talk about how we process the impossible as human beings, because that's really what's at stake here. When confronted with something like 3i Atlas, something that breaks the rules we've built our understanding, and we tend to go through predictable stages. First comes disbelief, the instinctive rejection that says, this can't be real. Then comes skepticism, the more rational response that demands evidence and verification. If the evidence holds up, we move to confusion, recognizing that our models don't fit, but not yet having new ones to replace them. Finally, if we're open-minded enough, we reach acceptance and begin the hard work of rebuilding our understanding. This pattern isn't new. We've seen it play out throughout scientific history. When Galileo observed the moons of Jupiter, the initial response from many was disbelief. They simply couldn't accept that Earth wasn't the center of all celestial motion. When Darwin proposed evolution by natural selection, the skepticism was intense, challenging deeply held beliefs about humanity's place in nature. When Einstein introduced relativity, even physicists struggled to accept concepts like time dilation and curved space-time. What's different with 3i Atlas is the speed at which these stages are unfolding. Amplified by our interconnected world and the sheer strangeness of the anomalies, we're moving from disbelief to acceptance in weeks rather than decades, partly because the evidence is accumulating so rapidly from multiple independent sources. But there's another factor at play to our collective readiness for paradigm change. The other scientific revolutions happening in 2025 have primed us to expect the unexpected. When dark stars are challenging our understanding of cosmic structure, when fusion is rewriting energy economics, when quantum teleportation is becoming practical, an anomalous comet feels less like an isolated oddity and more like part of a larger pattern of reality revealing its hidden layers. This psychological context matters because it affects how we interpret new data. A scientist who's already seen their field appended by unexpected results is more likely to approach new anomalies with curiosity rather than dismissal. A public that's been following these developments is more likely to engage with the mystery rather than dismiss it as too complicated or irrelevant to their lives. We're seeing this play out in real time with 3i Atlas, the scientific community isn't fragmenting into camps of believers and skeptics as much as it might have a decade ago. Instead, there's a remarkable openness to considering multiple possibilities, from exotic, natural explanations to more speculative hypotheses. The public discourse, while certainly containing its share of conspiracy theories and misinformation, also features genuine curiosity and engagement at a level we rarely see for astronomical discoveries. This creates a positive feedback loop. As more people engage seriously with the anomalies, more brain power gets applied to understanding them. As scientists feel supported in exploring unconventional ideas, they're more likely to push boundaries. As the media covers the story responsibly, focusing on the science rather than sensationalism, public understanding grows. All of this creates an environment where breakthrough thinking becomes more likely. But there's a danger here too. In our eagerness to embrace the revolutionary, we must maintain scientific rigor. Extraordinary claims still require extraordinary evidence. The fact that we're more open to unusual explanations doesn't mean we should lower our standards for what constitutes proof. The challenge is finding the balance between openness to new ideas and healthy skepticism. This is where the scientific method, properly applied, becomes more valuable than ever. It gives us tools to navigate between premature acceptance and closed-minded rejection, to evaluate evidence systematically, to distinguish between what we know, what we don't know, and what we currently think but might be wrong. 3i Atlas is becoming a case study in how science handles paradigm-challenging discoveries in the 21st century. The traditional model of scientific revolution where a lone genius overturns established thinking against resistance doesn't really fit our current reality. Instead, we're seeing something more collaborative, more distributed, more accelerated. Teams of researchers across multiple institutions and countries are working together, sharing data in real time, building on each other's findings. Citizen scientists are contributing observations and analysis. AI systems are identifying patterns humans might miss. The result is a kind of collective intelligence that's tackling these mysteries from multiple angles simultaneously. This doesn't mean individual breakthroughs won't happen. They will, and they'll be crucial. But they'll likely emerge within this collaborative context rather than in isolation. The next Einstein might not be a single person, but a network of researchers working together in ways we couldn't have imagined a generation ago. What's particularly exciting is that this isn't just about solving the puzzle of 3i Atlas. The methods we're developing, the approaches we're refining, the ways we're organizing scientific inquiry become templates for how we tackle other complex, multidisciplinary problems. Climate change, disease, sustainable energy, understanding consciousness, these all require the same kind of integrative thinking that 3i Atlas is forcing us to develop. In a sense, this comet is giving us a training ground for the big challenges ahead. It's teaching us how to handle uncertainty, how to work across boundaries, how to maintain scientific integrity while pushing the edges of knowledge. These lessons will serve us well long after 3i Atlas has continued its journey out of our solar system. The coming weeks will be crucial, as the spacecraft flybys provide new data, as analysis of existing observations deepens, as theoretical work explores possible explanations, we'll start to see which paths lead to productive understanding and which turn out to be dead ends. But whatever the outcome, we're already learning something valuable about how science can and should work in the face of the truly unknown. That might be 3i Atlas's most important gift to us, not the specific answers it provides, but the questions it forces us to ask. Not just about comets, but about how we pursue knowledge itself. Let's zoom in on the human element for a moment. Because science isn't just about data and theories, it's about people, passions, and the messy, beautiful process of discovery. The story of 3i Atlas is being written by hundreds of researchers around the world, each bringing their unique perspective, expertise, and even their quirks to the puzzle. There's Dr. Alina Rodriguez at the European Southern Observatory, who has barely slept since the first images of the Sunward Jet arrived, spending nights in front of her computer screen, tweaking image processing algorithms, looking for any artifact that might explain the impossible. Her colleagues joke that she has a personal relationship with the comet now, that she talks to it as if it might answer back. But there's something touching about her dedication. This isn't just a professional challenge for her. It's become personal, a quest to understand something that defies everything she thought she knew. Then there's Professor Marcus Chun, a spectroscopist at the University of Arizona, who first noticed the extreme nickel-to-iron ratio. He's a methodical, cautious scientist who usually avoids grand statements. But even he can't hide his excitement when discussing the chemistry. In a recent interview, he compared the feeling to being a detective who's stumbled upon a clue that doesn't fit any known case file. "You know, there's a story here," he said, "but you have no idea what kind of story it is yet." Across the Pacific, Dr. Yuki Tanaka leads a team in Japan that has been analyzing the 4-hour pulse using techniques borrowed from seismology. They're treating the comet's brightness variations like earthquake waves, looking for patterns that might reveal internal structure. It's an unconventional approach, but then again, this is an unconventional comet. What's fascinating is how these researchers, despite being spread across continents and working in different subfields, have formed a kind of informal network, sharing data in real time, challenging each other's interpretations, building on each other's insights. In an era of competitive science and publish or perish pressures, this collaboration stands out as something special. It's not that there's no competition, there is, and it's healthy, but there's also a recognition that this mystery is bigger than any individual or institution. The human stories extend beyond the professional researchers too. Amateur astronomers have played a crucial role, providing additional observations that help fill gaps in professional coverage. There's something inspiring about people in their backyards, with telescopes they bought with their own money, contributing to cutting-edge science. One amateur in Australia, a retired teacher named Michael, has been tracking the comet's brightness variations with such precision that his data is being cited in professional papers. When asked why he spends his nights this way, he simply said, "How could you not? This is history happening." The public engagement has been remarkable too. The YouTube channel covering this story has millions of subscribers, with viewers from over 100 countries. The comment sections are filled with thoughtful questions, creative hypotheses, and genuine wonder. Sure, there's misinformation and wild speculation too, but there's also a collective sense of participating in something important. This engagement matters because it creates social support for the scientific process. When the public is invested in discoveries like this, it's more likely to support the funding and patience that good science requires. It also helps create the next generation of scientist kids. Watching these videos might be inspired to pursue astronomy, chemistry, or physics because they've seen how exciting and mysterious the universe can be. What's particularly touching is how this has become a human story across borders and cultures. In a world often divided by differences, 3i Atlas has become something that unites people in wonder and curiosity. The same images that captivate scientists in Chile are mesmerizing students in Nigeria, office workers in Japan, farmers in Nebraska. There's something universal about confronting the unknown together. The emotional journey of this discovery mirrors the scientific one. There have been moments of frustration when data seemed contradictory, periods of anxiety when funding for observations was uncertain, times of disappointment when expected results didn't materialize. But there have also been moments of pure joy, aha moments when a piece of the puzzle suddenly fits. The shared excitement when a new observation confirms a hypothesis. The quiet satisfaction of contributing to human knowledge. These emotional dimensions aren't secondary to the science, they're integral to it. Science is a human endeavor driven by curiosity, passion, creativity, and perseverance. The story of 3i Atlas reminds us of that, showing us the faces behind the data, the dedication behind the discoveries, as we await the results from the spacecraft flybys. It's worth remembering that whatever those results show, the human story of this investigation is already a success. It has demonstrated how science can work at its best, collaborative, rigorous, open to new ideas, driven by wonder. It has shown us that in an age of specialization and silos, we can still come together across boundaries to tackle big questions. And it has reminded us that the universe, in all its complexity and mystery, has the power to unite us in shared curiosity and awe. The coming weeks will bring new data, new insights, and probably new questions. But whatever the scientific outcomes, the human story of 3i Atlas will remain a testament to what we can achieve when we combine our individual strengths in pursuit of collective understanding. That might be the most important lesson of all that. The greatest discoveries aren't just about what we find in the cosmos, but about what we discover in ourselves along the way. Let's talk about what comes next, not just in terms of scientific investigation, but in terms of how this discovery might ripple through our culture, our technology, and even our philosophy. The implications of 3i Atlas extend far beyond astronomy, touching on fundamental questions about our place in the universe and how we understand reality itself. First, consider the technological impact. The challenges posed by studying this object have already driven innovation in observation, techniques, data processing, and theoretical modeling. The image processing methods developed to enhance the sunward jet without creating artifacts have been applied in other fields, from medical imaging to climate data analysis. The AI systems trained on cometry data are finding applications in completely different domains, from financial modeling to drug discovery. The collaborative platforms developed for sharing real-time observations across continents are inspiring. New approaches to international scientific cooperation on other urgent problems. But the technological impact goes deeper. The anomalies we're seeing with 3i Atlas might inspire entirely new lines of research and development. If the rhythmic outgassing turns out to have an engineered component, It could revolutionize how we think about propulsion systems for space exploration. Even if it's natural, understanding how a small body can regulate its activity so precisely might inspire new approaches to controlling chemical processes or energy systems. The unusual chemistry, particularly the nickel dominance and carbon dioxide excess, could lead to new insights into materials science. If we discover natural processes that create these unusual ratios, we might be able to replicate them for industrial applications. If we find evidence of engineered materials, the implications are even more profound, would suggest manufacturing techniques far beyond our current capabilities. The quantum connections we've explored might inspire new approaches to information processing and communication. The possibility that quantum effects play a role in the comet's behavior could open up entirely new research directions at the intersection of quantum physics and astrophysics. Beyond technology, consider the cultural impact. 3 Atlas has captured public imagination in a way few astronomical discoveries have. It's not just another comet or asteroid. It's something that challenges our understanding, that invites us to question what we thought we knew. This has sparked conversations in classrooms, around dinner tables, and across social media about the nature of scientific knowledge and how we respond to the unexpected. We're seeing a resurgence of interest in science education, with enrollment in astronomy and physics programs reportedly up since the discovery became public. Science museums are developing exhibits around the mystery, using it as a way to engage the public in the scientific process. Popular culture is responding to with documentaries, books, and even fictional treatments exploring the implications. This cultural engagement matters because it creates a more scientifically literate society, better equipped to understand and address complex challenges. It also fosters the kind of curiosity and wonder that drives scientific progress in the US. Long-term, philosophically, 3I Atlas raises profound questions about how we understand the universe and our place in it. If this object turns out to be natural but unlike anything we've seen before, it would suggest that the universe is far more diverse and creative than we imagined. It would be a reminder that nature has produced phenomena beyond our current comprehension, and that there's always more to learn. If, on the other hand, evidence emerges suggesting artificial origin, the philosophical implications would be even more profound. It would fundamentally change our understanding of our place in the cosmos, potentially answering one of humanity's oldest questions: are we alone? Even the possibility that this might be the case forces us to confront big questions about how we would respond to such knowledge, how it would affect our societies, our belief systems, our sense of identity. But perhaps the most important philosophical implication is what this discovery teaches us about the nature of knowledge itself. 3 Atlas is demonstrating that scientific understanding is always provisional, always subject to revision in light of new evidence. It's showing us that the universe doesn't always conform to our expectations, and that the most exciting discoveries often come from the unexpected. This humility in the face of mystery, this willingness to question even our most fundamental assumptions, is perhaps the greatest gift that 3I Atlas offers us. It reminds us that science isn't about accumulating facts so much as it is about continuously refining our understanding, always recognizing that there's more to learn. As we move forward, the study of 3I Atlas will likely become a model for how we approach other complex, multidisciplinary problems. The methods we're developing, the collaborative approaches we're refining, the balance we're striking between openness and rigor, all of these will inform how we tackle other big challenges, from climate change to understanding consciousness. The coming months and years will bring new data, new insights, and probably new questions. But whatever we learn about 3i Atlas itself, the process of investigating it has already changed how we do science, how we engage the public with discovery, and how we think about our place in the universe. That might be the most lasting legacy of this mysterious visitor, reminder that the universe is full of wonders waiting to be discovered, and that the pursuit of understanding is one of humanity's noblest endeavors. As 3i Atlas continues its journey out of our solar system, carrying its secrets with it. It leaves behind not just scientific data, but a transformed understanding of what's possible when we combine curiosity, collaboration, and courage in the face of the unknown. That transformation will ripple through our science, our technology, and our culture for years to come, inspiring new generations to look up at the stars and ask, what else is out there waiting to be discovered? As we reach the end of this deep dive into the mysteries of 3i Atlas, it's worth taking a step back to appreciate the journey we've been on together. What began as a single anomalous Omega comet with a jet pointing toward the sun has blossomed into a multi-dimensional mystery that touches on physics, chemistry, technology, philosophy, and even the very nature of scientific discovery itself. We've explored 15 distinct anomalies, each one a puzzle piece that doesn't quite fit our existing understanding. We've considered explanations ranging from exotic natural processes to the possibility of engineered components. We've looked at how this discovery fits into a broader pattern of scientific revolutions happening in 2025, from dark stars to fusion energy to quantum teleportation. We've examined the human stories behind the science, the researchers dedicating their lives to understanding this object, the amateur astronomers contributing crucial observations, the public engaging with curiosity and wonder. We've considered the technological, cultural, and philosophical implications of whatever we ultimately discover about 3i Atlas. Through it all, one theme has emerged consistently. The universe is more complex, more surprising, and more wonderful than our current models allow. 3i Atlas is teaching us humility in the face of mystery, showing us that even in an age of remarkable scientific achievement, there are still phenomena that challenge our understanding and push us to think bigger. The coming weeks will be crucial as data from the Hera and Europa Clipper flybys arrives. These observations could confirm the anomalies, contradict them, or reveal entirely new aspects of the mystery. But whatever the results, we're already richer for the journey of investigation. The methods we've developed, the collaborations we've formed, the questions we've learned to ask, of these will serve us well as we continue exploring the cosmos and our place within it. What's particularly beautiful about this story is how it demonstrates the best of scientific inquiry at work. We've seen skepticism balanced with openness, rigor combined with creativity, individual expertise contributing to collective understanding. We've witnessed the scientific community embracing uncertainty while still demanding evidence, considering extraordinary possibilities while maintaining high standards for proof. This isn't just about solving the puzzle of one unusual comet. It's about modeling how we as a species, can approach the biggest questions and the most profound mysteries. It's about showing that curiosity, collaboration, and courage in the face of the unknown are among our most valuable qualities. As 3i Atlas continues its journey out of our solar system, it leaves behind not just scientific data, but a transformed understanding of what's possible when we combine these human qualities with the tools of modern science. The comet itself may remain mysterious in some respects forever, carrying its secrets into the vastness of interstellar space. But the impact of its visit will ripple through our science, our technology, and our culture for years to come. Perhaps the greatest lesson 3i Atlas offers us is this: the universe is full of surprises, and the most exciting discoveries often come when we least expect them. By staying curious, by working together, by maintaining both rigor and openness, we position ourselves to recognize and understand these surprises when they arrive. In a world that often feels divided and uncertain, the shared wonder of a cosmic mystery reminds us of what we can achieve when we unite in pursuit of knowledge. 3i Atlas has been more than just an astronomical object. It's been a catalyst for collaboration, a spark for imagination, a reminder that there's always more to learn about the universe and ourselves. As we conclude this exploration, the mystery isn't over, it's just entering a new phase. The data will continue to come in, the analysis will deepen, the theories will evolve, and we'll be here, watching, questioning, wondering, ready to follow the evidence wherever it leads. That's the promise and the beauty of science. It's an ongoing journey of discovery, with each answer leading to new questions, each mystery opening doors to deeper understanding. Thank you for joining this investigation into one of the most fascinating astronomical objects we've ever encountered. Your curiosity, your questions, your engagement have been part of this story too. As 3i Atlas fades from our view, it leaves behind not just scientific puzzles, but a renewed sense of wonder at the universe we inhabit, a universe that continues to surprise, inspire, and challenge us to expand the boundaries of knowledge. The next chapter of this story is being written now, by researchers around the world, by instruments in space, by AI systems analyzing data, and by curious minds like yours. Stay tuned, stay curious, and never stop looking up at the stars and asking what else is out there waiting to be discovered. The universe, after all, is full of mysteries, and each one we solve reveals new ones, inviting us deeper into the endless adventure of understanding. 3i Atlas is just one chapter in that adventure, but what a chapter it's been.